So continuing with sunlight, and a lot of the physics that we'll see with sunlight is very close to the physics we already saw with microwaves and radio waves for good reason. They're all just electromagnetic waves. They differ only in frequency and wavelength. Same idea. And where I kind of left off was the idea of color temperature. And I want to, since it's something that you can really use in real life, I want to make sure that I've done it properly and finished it. The sun is what's known as a black body. That is, its actual color is black. It absorbs all light that hits it. That's what black is. And objects that are black, that absorb all light that hits them, that doesn't mean that no electromagnetic waves are coming from them. They're not unable to send light at you, or light's relatives like radios and microwaves. What it means is that they absorb the ones that hit them, and they send out electromagnetic waves that are characteristic of only one thing, their temperature. Nothing else matters. It's purely statistical issue. Actually, it's got quantum mechanics in it too. It's a little messy. The origin of this behavior, what's called the black body spectrum, ultimately it's important to physicists, and it was important to the science of the early 20th century. But the idea is this: that the hotter, first off, the source of this what's called thermal radiation, and particularly from a black body, the black body spectrum, it comes about because the charged particles, everything's contains charged particles. The charged particles move about and undergo acceleration, which is the key to emitting an electromagnetic wave. And the hotter the object is, on average, the more vigorous the motions of all the charged particles become. So they're emitting electromagnetic waves of various frequencies and wavelengths based on the statistics of how fast this little charged particle is moving, that one, how much they bump into each other, what their accelerations are. So there's a spectrum that comes out for a given temperature. And for a temperature that is low, say not as hot as the sun, the temperature of an incandescent light bulb, like this guy, try again. This guy's got a hot filament in there. It's made of the metal tungsten, an optimized choice that was perfected in the beginning of the 20th century too. So it's made of tungsten. They can't heat it much hotter than this. It's heated electrically. This is you all at this point should understand why that's getting hot. We're running current through it. It's a poor conductor of electricity. It gets hot as the charges struggle to get through it. And it's about 2700 Kelvin. Kelvin is the temperature scale, just like Celsius, same spacing between degrees, except whereas Celsius hits 0 at the freezing point of water, melting point of ice, the Kelvin scale is shifted so that when it hits 0, that's so-called absolute 0. There is no thermal energy left to be extracted from something. So that's pretty cold. That's Celsius minus 273. So the 0 of Kelvin is shifted 273 degrees towards lower, higher. I have to think too hard. Okay, so that's about 2700 Kelvin. And at 2700 Kelvin, the word degree is omitted. It's just Kelvin. That's not very hot. I mean, it's hot, burn your fingers and all that stuff, but you can't go much hotter without damaging the filament. And so this thing emits a spectrum that's shifted towards lower frequencies because the vigorousness of the thermal motion in there is less than it would be in the sun, which is hotter. So this guy's got less vigorous thermal motion. The statistics give it a spectrum that I'll draw it here with my laser pointer. Remember, this is this weird scale where I've got wavelength on the bottom. On the x-axis, the horizontal axis, is both in wavelength and in frequency. They go together. If you multiply one by the other, you get the speed of light every time. So for this light, it's at relatively low frequencies, so it's beyond a lot of stuff over here at lower than 4 in these units, and longer wavelengths than 700. So the spectrum of this is sort of out here, and it comes rolling along like this. Can you sort of see the line I'm drawing here? What's the point of that? Most of the light waves that are coming out there, and there are lots of individual light waves, most of them are over here in the red end of the spectrum, and even out in the infrared. The fact that a lot of them are in the infrared, which we can't even see, indicates in part why these bulbs are being phased out. It's because they're very energy inefficient. This is a 25-watt bulb, which is not hugely energy consuming until you have to generate 25 watts yourself with your hand. That's hard work. You get tired. So it's consuming real amounts of power, but most of the energy is coming out not in the visible light, but rather in the infrared, which is useless. Big waste of the power. The takeaways that I hope you come off with is that not only is a lot of the light invisible to us, but not very much of the light is over here in the blue end of the spectrum. So these so-called incandescent light bulbs, where incandescent means it produces light by way of heat. That's all that incandescent means. There's not much blue. They are lousy at producing blue light. And so if you've ever seen colored light bulbs where they just put paint around the light bulb to pick out, to absorb parts of the spectrum and leave you with what's left. For example, if you put red paint over this, it will absorb all the blues and greens and leave you with the reds. Well, if you make 3 bulbs, one painted, say, red, and one of them painted green, and the other one painted blue, the blue one's going to be really dim because there wasn't much blue light coming off this hot filament. It's just not hot enough. It's very it's crummy blue content. And this has had all sorts of consequences. Colored lights up until, well, about the time a little before your birth, by and large, colored lights were essentially painted or filtered incandescent lights. And there wasn't much blue to work with. And so blue lights were always relatively dim. I think traffic lights, they use red and green, right? Which is kind of a crummy choice because there are people with color blindness who have trouble distinguishing red and green. Why pick exactly those colors? Why not use blue? Well, it's because blue lights are relatively dim. You can't get a lot of oomph out of them. Nowadays you can, but that's modern technology, which we'll get to. It's different ways of making light. Don't use heat. Be more sophisticated in making light. Is it okay so far? So low temperature surfaces, where low is relative, it still burn you, but it's not hot like the sun, produce a spectrum that's shifted heavily towards the low frequency, long wavelength part of the spectrum, which we see as red light. So if I talk about shifting towards the red end of the spectrum, it's toward those longer wavelengths, lower frequencies, all right? So going to lower temperature shifts you towards the red. On the other hand, going to higher temperature with a hot surface shifts you more and more towards the blue end of the spectrum. So if you crank up the temperature, this tungsten filament would melt and become gaseous, actually. If we go to the temperature of the sun, now the spectrum, instead of being peaked over here in the infrared, it peaks somewhere, I think, in the green. It includes a lot of blue and a lot of red. It's really nice. The sun spectrum is right all around in this area. And the result is that it's got the whole mix of red and green and blue. And we can't make that with a hot surface easily in this here on Earth because everything's a gas at the temperature of the sun. It's hopeless. So we can pretend. This is using modern technology to synthesize a sun-like spectrum. It's not really a hot object. Obviously I can touch it. You've done this before. Anyway, the spectrum is sort of about the right range that it needs to be. And you can see with your eyes that it's got a much more blue to it than a tungsten filament. And so with this kind of bulb, no problem. If you want to filter that and make blue out of it, or otherwise, there's no problem. There's plenty of blue. Also okay? The last detail I want to say with this, and I said it last time, and I'll do it again, just for as a consumer of buying light bulbs, these light bulbs are used for illumination as opposed to fun games like a green light bulb. So set those aside. The ones that are supposedly producing white light, these are both defined as white light. They're obviously not the same spectra, but in different contexts, you can call them white. In modern days, they are sold according to color temperature. Whether the word color temperature is stated or not, it's in the minds of people who are making and selling these bulbs. And as you go to higher color temperature, this is low color temperature, it's 2700 Kelvin. And this is higher color temperature, it's actually 6,000 plus Kelvin. It's way up there. It's actually it's a little hotter than the sun, so it's got more blue in it than even the sun does. As you shift across there, you can see the difference in the appearance of the light. And for different places, different contexts, you want different colored lights. And so if it's supposed to be a romantic candlelight dinner, typically you'll go for the low color temperature, as though it were candlelight. Candles, incidentally, are about 1800 Kelvin. They're even cooler than tungsten. Colder than tungsten, therefore richer in reds than tungsten normally is. You can use a dimmer. If you dim it, you shift the color even to lower temperature. If you're trying to do a medical exam, you might want this. You get the sunlight. It's sickeningly blue, but it's okay. All right. Long ago, 40 years ago, give or take, the light bulbs like this, what are called fluorescent light bulbs, they're illuminating the room now. They'll eventually all go away. But the fluorescent light bulbs, the early ones in my childhood, they had not really gotten a good handle on how to produce nice simulations of thermal light, of light from a hot object. So they would try to piece together the right spectrum, and they did a bad job with it. And some of those early light bulbs were really pretty sickening. Some people had the sense of that fluorescent light bulbs were just so medicinal. They had much too much blue. They were like this. I mean, this is, you don't really want to illuminate your house. I mean, almost nothing wants to be illuminated with that. And so as time went by, people would make better and better colors, simulations of thermal light. And now they're quite good. You can get what's called warm white, cool white, deluxe warm white, deluxe cool light. But even that's all dying off because they're going to all be replaced by light-emitting diodes, which is just the newer technology. All right, my story about color temperature. Okay. Any thoughts or questions? Your camera also cares about color temperature. It's typically your cell phone, when it's taking pictures, it's trying to say, is this scene illuminated with daylight, like with high color temperature, or is it illuminated by light bulbs, incandescent light bulbs, which is low color temperature? Because it's trying to make a picture that looks right in any context. And if it makes a wrong guess, for example, if it thinks that you're in daylight and you're actually illuminated in incandescent light bulb, low color temperature illumination, the picture will come out orange because it will have assumed there was a lot of blue illumination that it actually isn't there. And vice versa, the other way around, with pictures that are way too blue. So much of the technology now solves these color temperature problems for you, but if you have a camera that has color temperature adjustments and stuff, or if you become a cinematographer, videographer, whatever, you want to pay attention to color temperature. And the classic way on the set, people will take out a sheet of a white surface and send the local light at the camera. The camera will look at that light and say, I'm looking at a white surface. This is how it looks in the current illumination. Camera, figure out the color temperature, and the camera will do that. All right? I'll stop. Okay. How does the sun surface emit light? You should know this at this point. I've talked about enough. How many think, A, its hot atoms glow with their characteristic colors, like those of a neon sign? No, that's certainly not the main source. There's a little bit of that, but not much. B, its hot atoms escape from the surface and become light waves. No. Atoms and light waves are not the same thing. You can't turn one into the other. Thermal energy causes its charged particles to accelerate rapidly and thus emit electromagnetic waves. Yeah, thank you. Good. All right, action. The spectrum of sunlight, I've talked about this. This actually now shows you the spectrum for the sun itself, which has a color temperature of about 5,800 Kelvin. And there's some infrared light here, which you see in the drawing. You can't see it with your eyes. You feel it as heat. It makes things hot. They absorb it, and the power associated with absorbing that incoming infrared light warms things up. But it really, the intensity peaks in the visible, which is, it's not a coincidence. We evolved in an environment with the sun around us, so we developed, our sight developed to see this particular part of the spectrum. And then there's a part of the spectrum coming from the sun that we cannot see. It's beyond violet, it's called ultraviolet. This is problematic, as you'll see, for us. We don't see it, okay? It can cause damage to us. We'll see later on that it is, I told you last time, it's called ionizing radiation. It's capable of causing molecular damage directly. And we don't really want to be exposed to it to any great extent. Yeah, you can go out and get a tan, but that's really your skin responding to damage. It's trying to fix damage. The famous ozone layer that people worry about in different generations. You do want it up there because it absorbs. It's particularly able to block the tail end of the ultraviolet, the part that's the most potentially damaging watt for watt. So we don't want to have it down here on the Earth's surface, and thankfully the ozone's up there gobbling it up, turning it into thermal energy. All right? Incidentally, you don't know what ozone is. Ozone is just oxygen, but instead of being the two-atom oxygen molecule that you're used to, that you're breathing right now and makes life possible, it's the 3 oxygens tacked together. It's not particularly stable. I was making it with that Tesla coil we had in there a couple weeks ago, where it was shooting the sparks out. It creates ozone beautifully, and so if you smelled sort of a chlorine-y smell, a kind of spicy reactive smell after it, that was ozone. All right, so 5,800 Kelvin, we see that as white light. This is the same story, different colors. I'm not going to ask that question. What else do we want to go here? Okay, now we'll get into stuff that actually is more important. When a light wave encounters an atom, so you've got an atom sitting there with its positively charged nucleus and its negatively charged electron cloud, if you will, around it. We'll talk more about what that cloud is like later. Not today. When that electric field comes roaring along, what does it do to this atom? Okay? How many things? It says it polarizes the atom slightly, which is to say, yeah, so it's giving you the answer. Different colors, because I can't. So the atom, when it's sitting there all by itself, basically it's got some negative charge, it's got some positive charge. The negative charge is centered pretty well on the atom, on the positive charge, so there's, for an atom, there's no net electric polarization. It's not like they're separated. But if an electric field comes along and pushes on this thing, it'll pull the charges apart a little bit. And if the electric field reverses, it'll pull them the other way and back and forth. So the atom itself is becoming a polarized object with positive and negative charges that are flipping up and down as the wave goes by, in sync with the wave. Is that okay? So what do you think can happen? So the atom can absorb and re-emit the wave. How about that? This is a terrible question. But the atom cannot absorb the wave. Nah. I don't know why I still have this one on there. A was the right answer. Everybody put your hand up. Yeah. Sometimes I don't edit my own work properly. Bottom line is that the passing electromagnetic wave is fine in empty space. It is quite capable of traveling through empty space, and nothing bothers it. And recent experiments have indicated that it travels perfectly well across unbelievable stretches of the universe at the famous speed of light. Nothing changes in it. However, when it encounters an atom, it does indeed polarize the atom. That electric field causes the atom's positive stuff to go one way, the negative stuff to go the other way, and the stuff jiggles in sync with the passing wave. And that allows the atom to take in part of the wave and re-emit it some other direction. So light can scatter off little pieces of matter, like an atom, or all the relatives of atoms, like molecules, little dust particles and stuff. So what's important here is that light is, when it first encounters, for example, the Earth's atmosphere, it doesn't travel so simply anymore, because it starts to polarize the material it travels through. You okay with the idea that it polarizes stuff? Are there questions about that? The more charges there are around, the more polarization occurs. So this is leading into this question, which is, why does the sky appear blue? In the sky, the bottom line is going to be the sky appears blue because part of the sunlight that was supposed to go one direction interacts with material en route in the air and changes its direction. And the stuff that preferentially, the stuff that gets redirected is at the high frequency end of the spectrum, the blue stuff. And that redirection gives this overall glow to the sky. So that's where we're going with this. The details are as follows. When a light wave comes along and encounters some little object, whether it's an atom or a molecule or other things, doesn't matter yet, it causes polarization in that object. And that polarization process takes energy, because pulling positive and negative charge apart consumes some energy. So the light wave comes in, some of its energy gets involved in the atom, and then eventually the light wave is going to be gone, so eventually the atom's not going to have that energy. So the light wave goes into the atom and it comes back out. It doesn't have to come back out as the original light wave. Some of this is entangled with quantum mechanics, which is not the topic of the moment. But what's coming at us from the sun is countless individual light waves, tiny little ones, each one associated with a particular emission from one charged particle on the sun's surface. So they're little tiny waves. They carry tiny amounts of energy, each one. And the particles that they encounter effectively either let them go by unscathed. The energy goes into the atom for a little while and comes back out. Or the energy goes into the atom and it comes out in a new direction. It's redirected, having sort of gone in, jiggled charge up and down on what's kind of like an antenna, and then it gets retransmitted in a new direction. And that redirecting process by tiny, tiny antenna-like structures is called Rayleigh scattering, after Lord Rayleigh, prominent scientist of his time, or important scientist of the time, or whatever you want to call it. Anyway, it's that sort of somewhat absorption and re-emission process is Rayleigh scattering. And it's done by really tiny particles. In fact, it's okay. So is it atoms? Well, actually, it's not really atoms alone, because atoms are so small compared to the wavelengths of visible light. Visible light's wavelengths, from a human scale, they're tiny. They're less than a millionth of a meter, what's called a micron. They're below a micron in wavelength. So it's tiny, but that's still big compared to an atom. An atom's a factor of 500 smaller, maybe 1,000 smaller. So it's really dinky. Atoms are too small. So atoms, if you remember, for an antenna to be resonant at a particular wavelength, you want the antenna that is resonant so that it really interacts beautifully with an electromagnetic wave. You want that antenna to be half a wavelength long if you've got both halves of it, or a quarter wavelength if it's above a conductor. Well, these atoms, they're trying to act as antennas, and they're trying to be resonant if they can, but they're too small. By a factor of 50 or 100, they're really, really too small. So the consequence is that the light waves go and interact with the atoms, and the atoms go, I'm sorry, I can't take you in and send you a new direction. It just doesn't work. But sometimes you get molecules, or you get little agglomerations of atoms where for some fluke reason a bunch of atoms are all sort of packed together, which happens in our atmosphere, or it's a little dust particle. I mean, really little, like littler than you normally see. But the air is full of them, or a little water droplet. Those things get to be big enough that they can they can polarize to some extent resonantly and get a lot of charge moving and absorb the incoming wave and re-emit it. But they do that best for the waves that have the shortest wavelengths in the visible spectrum, the blue end of the spectrum. The blue end of the spectrum has a short wavelength. It's short enough in wavelength that it starts to see these little particles as decent antennas. Not great, but tolerably good. The red end of the spectrum with its long wavelengths just ignores those particles. They're too tiny, we don't care. So that means that the blue end of the spectrum is the part that is most likely to interact with the little teeny particles that occupy our universe, our atmosphere. And when that happens, they get involved with them and they get re-emitted. The direction is not completely random. It has to do with antenna effects. Remember, you get vertical polarization, all that kind of stuff from antennas. It all happens in these charged particles, in these tiny particles, and the light gets redirected. And so you get Rayleigh scattering. And I'm going to show you Rayleigh scattering two ways, but I want to make sure that you understand where does the blue sky come from? Before I do it, if you imagine that the sunlight has been coming 8 light minutes across space, it's, what is it, 93 million miles or 90, one of those numbers you learn in grade school. Quite a distance through empty space, no problem. But once it hits the Earth's atmosphere, it goes through some number of kilometers of the Earth's atmosphere. And even though this Rayleigh scattering process is very weak in the Earth's atmosphere, the density of those little particles is tiny. So you get a little scattering. What happens is that if you look up at the sun, there's the sun up there, and you see the light that managed to go through the atmosphere without getting scattered. It made the straight shot. So it's going to include most of the red light and all of the light that is in the blue end of the spectrum but wasn't scattered. But if you look elsewhere in the sky where the sun isn't, now you start to see the light that was destined for somebody else's eyes in a straight shot but didn't make it, was redirected. So all that blue light you see up there was light that did scatter, that did not go in a straight line and reach its original destination. Instead, it was sent off in new directions. I mean, some of it goes off into space, some of it goes to here, there, and everywhere, but you get your fraction. It comes into your eyes from light that didn't make a straight shot. You okay with that idea? Different places in the sky have different brightnesses. A lot of them have to do with geometry issues and how antennas work. And there's polarization in it too. Yeah, Fiona?
What changes in the sky then, during sunsets and sunrises?
Yes, so what changes in the sky during sunrises and sunsets? The length of the distance through which the sunlight has to pass changes. On noon, on the equator or whatever, when the sun is directly overhead, which is not a trivial thing to have happen. When it's directly overhead, the sunlight punches straight through the Earth's atmosphere. It travels the shortest distance. Its opportunities to get redirected are minimized. So that's the point where the glow of the sky is weakest. Does that make sense, everybody? But when the sun is low on the horizon at sunrise and sunset, it's got to travel through the layer. It's traveling through the layer of our atmosphere, which is some number of kilometers thick, at a shallow angle. So it has to burrow through it for a very long distance, and that gives ample opportunity for the light to get scattered away. So the amount of light that's left that manages to go by way of a straight shot to your eye gets weaker and weaker as the sun gets lower on the horizon, either at sunrise or sunset. Is that okay with everybody? Furthermore, it's preferentially red light that makes it through, which is why the sun looks red at sunrise and sunset. And I'll show you all these things. So far, it's all good? Let me show you. This one's easy because I can wave it around. So this is a block of silicone, a raw silicone rubber, so it's not actually a solid yet. It's weird what it is. It is. You can pull it out. It's kind of like a putty. But it has tiny particles in it that are responsible for giving silicon rubber its strength. They're little particles of basically of like quartz. It's not quartz the crystal. It's a different. The details don't matter. I'm lost in. But the particles are in there, and they are very good at Rayleigh scattering, and there are a lot of them. So this is the equivalent of a lot of miles of the Earth's atmosphere. And if I shine white light, this is just a, oh come on, pretty much white light into there, you see a lot of Rayleigh scattering near the flashlight. You see blue. Is that pretty much okay with everybody? The blue light gets preferentially scattered towards your eyes because it's the shortest wavelength, and the particles, which are tiny, they're small on the scale of light, they're best at scattering that stuff. They make decent antennas for it. The red light, not so much. As you go farther and farther into the block, it starts turning reddish. And the reason for that is because the blue light's already been picked off early. It's not there anymore. In fact, by the time you come out of the block, there's pretty much only red light left. Is that okay? You can see this, that's the sunset. The blue light's missing. It's been sent off left and right and up and down. All right? So we can do the same thing when it's more fun. This one's more, that one is just static, nothing changes. This one, actually I want to take this off too. All right. So this is a liquid. It's not, I guess this is good. Not just water. And what we're going to do is we're going to grow tiny particles inside it. So I need to turn off that screen. How do I do that? Oh yeah. Okay. So you're looking through the water from a light bulb below, which is missing. It's incandescent light bulb, not a lot of blue. Sorry. So it goes up. It goes off this overhead projector mirror, and there it is on the screen. And what I'll do is I'll start to grow tiny particles inside the water. 1, 2, 3. That's it. So they take a couple minutes to grow, grand total. And what you'll see as this happens is as the particles begin to appear and get large enough to do Rayleigh scattering, you'll start to see a blue glow here, a blue haze appear in the beaker as the particles begin to send off some of the short wavelength parts of the light. And that'll get stronger and stronger, and as it gets stronger, there will be less and less blue light making it up onto the screen, and the screen will get redder and redder. It's like the sun setting. Okay? Eventually, now it's already happening here. You're starting to see the scattering. There's just sort of a glow in the water that wasn't there when I first started. It's a bluish glow. It's a bluish haze of Rayleigh scattering. It's essentially developing like this, but in the water. They'll get larger and larger, and as they get larger, they eventually grow to the size where they begin to be like a half wavelength long antenna. They get pretty good at scattering all the colors. And instead of having a bluish haze here and a reddish glow up there, it'll start to go whitish because all the colors will be scattered. And it will develop to the point where once the particles are big enough, they're on the order of the size of the wavelength of light or bigger, everything scatters and it starts going white. It's like a fog. That's what are you seeing in a cloud or fog? You're seeing light being scattered by particles that are big enough. They're not doing Rayleigh scattering anymore. They're plenty big to be great antennas, and they're redirecting all the colors equally, and you get white light, white reflection. Okay, so when the sun's setting away here. Any questions about how this is working? Yeah, Jesse? What did I put in the beaker? It's a mixture of fixer from photographic fixer, which is sodium thiosulfate, and sulfuric acid. And the two react, and they're growing tiny crystals. And I keep looking up, every year or two I look up what crystals that are growing. They're water insoluble. It's taking chemicals that dissolve in water, and it's growing up chemicals that are not soluble in water. So they come out of solution, they're precipitating, and they're getting bigger and bigger, and they grow slowly. Is that okay? It's not a obvious thing like you can do it yourself. It's kind of like, you have to go get the chemicals. But anytime you make little teeny particles, if they're ultrafine, if they're much smaller than the wavelength of light, you'll get Rayleigh scattering. If they're on the order of the wavelength of light or bigger, you'll get what's called me scattering. You'll get scattering where it's color indifferent. And you've seen that your whole life. Most of the white things you see around you are essentially contain particles that are big enough that they me scatter. They cause indifferent scattering. And that's how you take any transparent material like glass, sugar, salt, quartz, you smash it. If you smash it not too finely, you smash it very finely, you get it goes white. It's the scattering off all the particles. Okay, the sun's pretty much set there. This guy's going to go white pretty soon. It goes through some interesting colors, and you've seen some of that coloring in the sky, depending on when things happen that add particles to the air. You get interesting scattering effects. For example, post-forest fires, post-volcanic eruptions, you can get very intense sky coloring where the scattering of light is either really intense Rayleigh scattering or it includes other kinds of scattering. But the other thing I was thinking is that on days when when the air is very dry, not much moisture in it, the sky can go almost black because the Rayleigh scattering becomes pretty rare. There's not much water in there. Water contributes a lot to the little particles that do the scattering. So if you have no water in the air, the sky can go really dark blue. If it's kind of humid and all that, you get a lot of particles up there, some of which are pretty big. The sky is kind of a pastel blue. It's got the blue to it because of Rayleigh scattering, but it's also got particles that are pretty big and indifferent to color, and then they wash out the rich blue. All right? Okay, call it a day. The sun has set. Okay. This is just what I told you. It's anything worth noticing here that I've forgotten? Not really. Yeah, so if you go to some other science fiction movies, will have planets that'll have green skies or something like that. No, you can't do that. I mean, the blue isn't there because of some special aspect of the Earth's atmosphere. It's the shorter wavelength band. You don't get a single color because it's not illuminated with a single color. It's illuminated by sunlight, which has this interesting spectrum, and if you preferentially scatter the purple end, the violet end of it, you get this new spectrum that is the blue of our sky. And it's going to be the blue of other planets' skies as well. All right? Yeah, I already forget it. Okay, so the rainbow. Where does the rainbow come from? And the story behind the rainbow begins with once light is passing through the Earth's atmosphere, it is undergoing Rayleigh scattering. That was the story that we just finished, but it also is doing other things. It is polarizing the particles through which it travels. And if you look at what happens during that polarization effect, so suppose a light wave is traveling along here, and I've got my little particle of any sort. It might be an air molecule, it might be a little water droplet, doesn't matter. This thing polarizes. Each time the electric field is up, the positive charge is pushed up. I'll leave the negative charge because I'm out of hands. But whenever the electric field coming along is pushing up, the charge is pushed up. It accelerates upward. And whenever the electric field turns downward, the charge accelerates downward, which means it slows to a stop and it starts to go back. And then the electric field flips. There's what I want to, can I do this right? The chart, forces cause accelerations. So the charge is bobbing up and down, and it's bobbing up and down sort of delayed compared to the electric field. So the electric field points up, the charge slows to a stop. It's really hard to do this, to think this through. What I'm trying to get across to you is, as the electromagnetic wave goes along, the charge bobs up and down, and the negative charge goes the other way. But it's delayed. The bobbing up and down is delayed because the electromagnetic wave causes acceleration, not immediate movement of the charge. The charge is lingering behind, lagging behind the electric field. The consequence of that is the charge is behind the field, and it's kind of playing with the wave as it goes by. The wave is giving it energy, and then it gives the energy back. And then the wave gives it energy, gives the energy back. The polarizing particles play with the wave, and they linger with, they cause it to linger and lag. They hold it back, which is, now I'm hand waving, but it is the case. The wave slows down. It gets delayed by its interaction with the charged particles in matter. In air, there are not that many charged particles per cubic meter, so the lagging effect is modest. But once you get into things like water or glass or diamond, the lagging becomes quite severe. And that effect, where the light literally slows down, the wave goes slower, its wavelength gets shorter. All the crests have to keep going by at the same rate as usual. The frequency doesn't change. But if the wave slows down, its crests get closer together. So the wavelength of, pick a color, green, which is about 500 nanometer long. In open space, it's 500 nanometers is the wavelength, but in water, it might be down to 370 nanometers. It shrinks, or 400 nanometers. The wavelength gets shorter. And the wave takes longer. If you watch the crests going by, they're just not moving as fast. So it's now moving at the speed at which light travels in a material. This is not the official speed of light. This is a new speed with no interesting fundamental importance. So when light encounters air, it slows down a little bit, like a part in 10,000, give or take. It's pretty small. And when it encounters water, it slows down by like 30%, I think, give or take. It's significant. It goes into diamond, it slows down by more than a factor of 2. It's traveling only 40% of its original official empty space speed because of this polarization effect and the lagging behind. You okay with that idea, or questions about that idea? The extent to which light slows down is characterized by a quantity known as the index of refraction. It's a value always greater than 1, except in exotic situations. Meaning that it's the ratio of the actual speed in the material to the speed of light. 1 over that. Divide the speed of light by the actual speed in the material. That way you get a value greater than 1. Okay? So with air, it's a little bit, that ratio is a little bit larger than 1. With diamond, that ratio is significantly larger than 1, more like 2.4, I think. Okay? Index of refraction. That's part A. So officially, I'm trying to tell you how a rainbow works, and that's my goal. Oh, incidentally, white. Remember I told you it would go white? The particles got really big. So, like all these white things, it's white because it's full of surfaces and particles, and the light scatters, and color doesn't matter. Okay, so back to this. Going towards how a rainbow works. To understand how a rainbow works, first you have to see that light slows down when it goes into a material like water. That's item 1. Item 2 is that when light makes a transition, actually I want to put one more thing in this. Light slows down. That index of refraction is always greater than 1. The color actually matters a little bit. The speed at which light travels through a material depends a little bit on the color of the light, because the higher the frequency of the light, the more able the charges are to play with it. The more intensely they play with it. They actually start to hit resonances where they really play with it. The resonances in clear materials like water or glass are not visible to you. They occur in the ultraviolet. But there's enough of a lingering effect of those ultraviolet resonances to mean that when you get close to ultraviolet, like into the blues really, the particles, the components of the material really play with the light a lot, and they slow it down a lot. Bottom line, you can ignore what I just said, except that the blue end of the spectrum typically travels a little slower in materials than the red end of the spectrum. All right? That'll become important. That is known technically as dispersion. it allows the colors to be dispersed. All right. Where I want to go with this is when a light wave encounters a surface and the polarization is outside and inside that surface are different. So the speed at which light travels inside and outside that surface is different. There are echoes that occur. That's actually, yeah. You can get reflections and you can get refractions. The light doesn't just blithely pass from one material to the other. After all, it's changing speed in going from one to the other. And that changing speed, first off, changes its wavelength. So how do you fit the new wavelengths in? That's a little bit messy. And trying to, right at that interface where the polarization on one side is strong and on the other side is weak, there's an upset there, and the absorption and re-emission of light is kind of upset at that point. And you get partial reflection, and you get refraction otherwise. Refraction occurs when light goes through a surface. So for example, just pick one just be specific, air and water. When light goes into that surface, leaving air, in which it travels quite fast, into water where it travels much slower, if it goes straight in, it continues straight on through the interface. But if it goes in at an angle, it enters the water at an angle, the path it travels after it goes in bends. And this has in part to do with the wavelength changing, and so the whole structure of the wave has to change. So it travels in a new direction to some extent. And I can show you this, that refraction effect. And to do that, I want to look down, document camera, side there. So now you're looking down on this block of plastic, and I'm going to send light through it. Dun, da, da, there's light. Okay, and if I dim the lights to this point, you can see it better. So you'll see the light rays are traveling fast through air, and then they enter the plastic, which is very similar to water. Again, it's transparent. It has resonances in the ultraviolet, which you can forget I said, that cause it to, that's a different topic. I'm confused myself. I didn't say anything. Roll it back a minute. I need post-production. No, sorry. Anyway, so the light goes in and it bends. It's traveling a new direction once it's inside the plastic. That's refraction, the bending of light. It depends on the angle at which it encountered the surface. The angle in which it left the surface is related by it's associated with the differences in the index of refractions of these two materials. So there's the refraction effect. That's the main, here I'm rambling, but that's the main point. You'll see also when the light leaves the plastic for the air, it bends again. The general rule, which is the only piece that I really care that you remember, is that when light slows down, as it does on this side of the system, in going into the plastic, when light slows down, it bends toward the perpendicular to the interface. That is, the perpendicular to the interface is this line like this. The interface is that flat surface of plastic, and this line that I'm showing you is perpendicular to that plastic edge. So the light in slowing down in the plastic bends toward that perpendicular line. Hopefully you can just see that. Any questions about that idea? When it speeds up, in this case, when it exits the plastic, it bends away from the perpendicular. All right? So that is refraction. It certainly occurs in raindrops when light from the sun hits it, which is part of how a rainbow is made. The other thing I want to show you before we finish here is reflection. Whenever a wave passes through an interface and changes speed also, part of it reflects off the surface. And you can see the reflections up here. They're not very strong. It's a partial reflection, but it's there. And that reflection has to do with how much the light changed speed. The more it changes speed, the more severe that reflection will be. So if light changes speed a lot, as it does, for example, in entering or exiting a diamond, then there's a pretty strong reflection, which is part of the reason why diamonds are sparkly. Okay, so with telling you how rainbows work, we will see that light undergoes refractions and reflections in going through raindrops. That's part of how light gets redirected. And the last piece is the speed with which light travels in water is not the same for all colors. So the colors get separated during this process. And I'll flesh it out on Friday. But it's that dispersion effect that separates the colors that creates the rainbow colors. So more later.
Thank you.
Thanks.